2-DG has long been a star in the world of anti-cancer drugs. Short for 2-deoxyglucose, this simple sugar is thought to work by disrupting the breakdown of glucose, a process that powers the growth of any cell, but the growth of energy-hungry cancer cells in particular. Put simply, 2-DG robs cancer cells of their molecular fuel. But a new study begs to differ. 2-DG, the authors of the study argue, is an effective anti-cancer drug, but not because it tampers and stalls tumors' metabolism. Quite the opposite. It sends that metabolism into overdrive, depleting cancer cells of the precious antioxidants that keep them alive. In this new model of how 2-DG operates, an enzyme called aldose reductase takes center stage. Tumor cells tend to overexpress this and another very similar-looking enzyme. Collectively, their job is to protect cancer cells by neutralizing toxic metabolites. Inhibiting these enzymes, therefore, has been proposed as one way to stop cancer growth. But the authors of the recent study propose a more effective strategy, boosting the energy-intensive production of these enzymes so much that it cripples the production of protective antioxidants. And that, they say, is where 2-DG comes in. As a substrate for aldose reductase, 2-DG modulates the enzyme's activity. So, more 2-DG should mean higher enzymatic activity, and thereby a lower capacity for cancer cells to churn out antioxidants. The team's results show precisely that. Cancer cells that tend to overexpress aldose reductase showed lower survival as the concentration of 2-DG was ramped up. To prove that the enzyme was in fact the lever acted on by 2-DG, the team inhibited the enzyme's expression in certain cells. As expected, that protected those cells from the otherwise damaging effects of 2-DG. Less of the enzyme translated to the greater survival. On the flip side, artificially kicking up enzyme expression made cancer cells more vulnerable to 2-DG. The results motivated the authors to explore a critical hypothesis. If stronger, less toxic substrates for aldose reductase than 2-DG can and do exist, then might those not make for better anti-cancer drugs? A head-to-head comparison between 2-DG and two substrates fitting that bill proved promising. The substrates, glyceraldehyde and diacetyl, showed significantly higher toxicity toward tumors grafted to mice, compromising their ability to grow to the same size and weight as non-treated tumors. The author's revision to the mechanism that drives 2-DG against cancer is subtle but crucial. With a renewed understanding of how the drug operates in the body, researchers can now begin to design a new class of powerful anti-cancer drugs that complement normal chemotherapy.